Alright, here we go with the Chapter 5 homework review. The topic of the week was moles and a lot of conversions involving them. So the average on this homework was about 9.7 out of 12, a little bit lower in the past, but not too terrible. But I suspect there's a lot of new topics that we're unfamiliar with that we need to gain familiarity with, get more comfortable with as we move forward, because these types of conversions are going to be useful for everything we're going to be doing in this chapter and the next chapter and even some beyond that. So let's go over a few things that we had some trouble with. So the first is a conversion involving moles. We want to know how many moles of hydrogen atoms are present in this huge number of molecules of CH4. Now I do apologize for us giving you this number in a weird format like this. I don't know, I didn't write this question, and for some reason they decided not to use scientific notation, which I suspect added to the difficulty. Because most calculators, especially at least the one I have, they don't have this many digits on them, so you have no choice but to convert this into scientific notation. So if we do that, we have to think about what we're looking for. We're looking for moles of hydrogen atoms. So whenever we're starting a problem like this, we want to keep in mind what it is we're looking for. So we're looking for a molar quantity, so keep that in mind, and then also that we're talking about hydrogen atoms, even though we're given a number of molecules of CH4. Alright, so if we have that many molecules of CH4, in scientific notation this number becomes 1.683 times 10 to the 25th molecules of CH4. We don't need all of those decimal places. That's way more precision than we'll need to get an accurate answer on this problem. So that's how many molecules of CH4 we have. Now there's two ways to think about this problem and how to do it. And what most of you recognized was that you need to use Avogadro's number. So we want to convert some moles of CH4. We just divide by Avogadro's number. So molecules of CH4 cancel out. Now we're in moles of CH4, but again, looking back at what we're asked for the moles of hydrogen atoms. In this formula CH4, this tells us that for every 1 mole of CH4, we have 4 moles of hydrogen. That's what the 4 tells us in that chemical formula. So we now need to include one more conversion, which is 4 moles of hydrogen for every 1 mole of CH4. And this is the step that a lot of you forgot to do, as I gather from talking to a few of you about this. So when we multiply this out, we should get 111.83 moles of hydrogen for this problem. Now the problem that you had may have had a different number of CH4 molecules to start with. This was one of those problems that has a variable input in it, so you're not going to necessarily have the exact same numbers, but you would follow this same approach. Now, as I said in class, sometimes it's possible to do these problems more than one way. And so another way to think about this problem, which will give you the same answer but just in a different order of operations, is if we're looking for moles of hydrogen atoms, we start with the same given quantity, 1.683 times 10 to the 25th CH4 molecules. Now remember that this chemical formula CH4 can be interpreted in terms of moles or in terms of individual atoms and molecules. So we could say that there are 4 hydrogen atoms per molecule of CH4. So this is an alternative way of interpreting this given information. So we could first convert to the number of hydrogen atoms, and then we still need to use Avogadro's number to convert into moles of hydrogen atoms. So we're not asking about the individual hydrogen atoms, we're asking for moles, which is Avogadro's number worth of hydrogen atoms. So we still need to convert into moles of hydrogen by dividing by Avogadro's number, just as we did before. So the same set of operations, just in a slightly different order. So the hydrogen atoms cancel out. Now we're in moles of hydrogen, which is what we want. And we will get the same answer, of course, because it's the same set of operations. Alright, so however you chose to think about this is fine. Both of these are equally valid and work just as well. But you do need to remember to multiply by 4 because there are 4 hydrogen atoms per CH4. So this then is a very similar one. This one had multiple choice, and I forgot to jot down the answer choices, so give me a second here. Alright, sorry for that pause. We're back, and we are going to finish this problem. So here's the answer choices that I've now written in by hand. So you had 5 choices here. One of them, choice A, It tells you how many molecules are in a 0.1 mole sample of ethane, and the rest of them tell you how many atoms would be in that sample. So we're going to have to calculate both of those quantities and see if they match up with any of these answer choices. So the key here is to realize that, again, when you use Avogadro's number, what exactly is it telling you? So if we're looking for the number of C2H6 molecules in this sample, so that would see if choice A is correct. So the number of molecules, we have 0.100 moles of C2H6, and this time we're going to multiply by Avogadro's number to get number of molecules. Okay, so this tells us we would have 6.02 times 10 to the 22nd molecules. Alright, so that does not answer choice A, so choice A cannot be correct. Now what we should realize is that when we use Avogadro's number, it's going to give us the number of fundamental particles in that sample. So for C2H6, which is a covalent compound, it's a molecular compound. When we multiply by Avogadro's number, that's going to tell us the number of molecules of C2H6. So if we want to find the number of atoms, we need to go one step further. So the total number of atoms, we have 6.02 times 10 to the 22nd molecules. We just figured that out in the previous step. Molecules of C2H6, and we have to multiply. So remember, C2H6, we have 2 carbons, 6 hydrogens, and that gives us a total of 8 atoms per molecule of C2H6. Okay, it's 8 total atoms. So we have 8 atoms per molecule of C2H6. And so when we multiply this out, we have to take that result from the previous one, 6.02 times 10 to the 22nd, and multiply it by 8. So the total number of atoms is going to be 4.82 times 10 to the 23rd, which matches choice B up here. Okay, so all the rest of these would be incorrect. So choice C, this 6.02 times 10 to the 22nd, that's the number of molecules, but there are 8 times that many atoms, and so on. Okay, so make sure we understand that difference and how to convert molecules into atoms or moles of molecules into moles of atoms and so on by using the chemical formula. So finally, one last one that involves this. Calculate the number of chlorine atoms that are present in 75 grams of dichloromethane, CH2Cl2. So here we're starting with a mass, so we have one more conversion to do. So if we're in grams of a substance, we know we're going to have to go through moles to get the number of atoms present, because that's what Avogadro's number refers to as moles. So we have to convert first mass into moles. And remember, the way we do that is using the molar mass. So the molar mass of CH2Cl2, it's the atomic mass of carbon, so we go to the periodic table here. Carbon is 12.01. Eventually this will let me write again. 12.01 grams per mole for carbon. We have 2 hydrogens, so the atomic mass of hydrogen is 1.008. And then we have 2 chlorines, so twice the atomic mass of chlorine. Chlorine is here 35.45, atomic number 17. Alright, so this is a review of atomic masses, which we learned at the beginning of the week, and how we can use those to determine the molar mass of a compound, which is what we need here. So if we add all those up, what we get is 84.93 grams per mole. Okay, so this is the molar mass of CH2Cl2, dichloromethane. So now we just have to do the conversion. So we're looking for the number of chlorine atoms. So we're starting with 75 grams of CH2Cl2. We have to first convert to moles. Okay, we're going to use Avogadro's number eventually, but we have to get into moles first. So we have 1 mole of CH2Cl2 as we just determined, is 84.93 grams. So that grams per mole, that molar mass, can give you that conversion into moles. Alright, we're in moles of CH2Cl2. Now we have a choice of a couple ways to do this, but one way to do it is, let's figure out how many CH2Cl2 molecules there are. So if we use Avogadro's number, 6.02 times 10 to the 23rd molecules of CH2Cl2 per 1 mole. But we're looking for, again, chlorine atoms. That's what we're targeting. So we have to do one more step, similar to what we saw in the last few problems, which is that each molecule of CH2Cl2 has 2 chlorine atoms. The formula is CH2Cl2. Okay, so 2 chlorine atoms per molecule. Molecules cancels out, and we are now able to convert into chlorine atoms. So just multiply this out. We get 1.06 times 10 to the 24th chlorine atoms, and the log of this, again, we have to get used to using the log key, is 24.03. Okay, that's how we would enter in the answer into Blackboard. Once again, this problem has variable input, so this starting mass here, 75 grams, you could have had a different number on your homework assignment if you got this problem, but the series of steps is still the same. So when we have a mass, we have to convert it into moles first before we can start using Avogadro's number. Alright. One other problem that we strangely had trouble with, this is a review from earlier in the course, and so I didn't cover it last week in class, is mass fraction. So remember, we can use mass percents and mass fractions to find molecular formula, but here we're not even going that far. So we just have a mineral that contains lead and sulfur. So lead is Pb, not that this really matters, but we have some formula involving lead and sulfur. We don't really need to know what the formula is, though, for this one, because we say that this we have 15.3 grams of, and then the lead in this sample is 9.80. Alright, so remember that the law of conservation of mass or definite proportion, either one of those, tells us that the sum of the masses of the elements has to equal the mass of the compound that forms from them. So we only have 2 elements here, which means that the mass of lead plus the mass of sulfur equals 15.3. And so if we want to find the mass of sulfur in this, we just take the total mass of the compound, 15.3 grams, subtract the mass of lead, 9.80 grams, and we get 5.5 grams. Alright, so now we have the mass of sulfur, because what we're asked for in this problem is the mass fraction of sulfur. So you have to remember the definition for mass fraction. The mass fraction is just going to be the mass of sulfur divided by the mass of the compound, which I'll abbreviate PbS in some ratio. So the mass of sulfur divided by the mass of the compound is going to give you the mass fraction. Now, a couple things here. First of all, because it's a mass fraction and not a mass percent, we don't want to multiply this by 100. If we were asked for mass percent, that's when you multiply it by 100. And also, when we say fraction, you still report it as a decimal. So don't try to type it in as a fraction. Just type in the decimal number that you get by dividing these. So when we divide these out, we get 5.5 grams for sulfur divided by 15.3 grams of the compound. And that's all we have to do. We don't have to do any more manipulations. So when we do that, if we round it to 2 significant figures, we get 0.36. So this would be the answer. We don't multiply that by 100. We don't try to report it as a fraction. Just enter in the decimal. That's it. Okay? So I think we made a little bit more out of that than was actually there. It's a very straightforward problem, and just remember the definition of mass fraction and how that differs from mass percent. Alright, finally, the last one that I got some questions about, and that we had a little bit of trouble with overall in our performance, is identifying an unknown element. So here we have a metal oxide with formula MO2 and it contains 21.23% oxygen by mass. Type the symbol for the element represented by M. So here this is our first of our unknown element problems. So we're going to see a lot of these as we go forward in the course, problems that involve identifying unknown elements. And when you want to do this type of problem, what you want to look for in an unknown element problem is find the atomic mass of that element, because then we can go to the periodic table and identify it. Alright, so if you know the atomic mass of your element, then you just have to go find it in the periodic table. So how do we find the atomic mass for an unknown element? We need two quantities. So remember that the atomic mass is the molar mass of an element, so it's going to be the grams of that element divided by the moles of that element. So if we can find the mass of the element in grams and we can find the number of moles, then we're good to go. Okay, so the way we approach this problem, then, we have to get both of these quantities to find the atomic mass. Okay. So to find the mass, it's pretty straightforward. We're given a mass percent of oxygen, so let's assume 100 grams of compound. So when we're doing problems like this involving mass percent, it's very convenient to assume 100 grams of compound, because then the mass percent tells you the grams of each element in that compound. So that means we'll have 21.23 grams of oxygen, and then the rest is going to be the metal, M. So if we have 100 minus 21.23, we would have 78.77 grams of our unknown M. Okay, so that's going to be the mass we put in here, 78.77. But now we need to figure out the number of moles that corresponds to. And the way we do this is a little bit trickier. So if we have 21.23 grams of oxygen, we can convert that into moles. So the moles of our unknown M, we have 21.23 grams of oxygen. The atomic mass of oxygen is 16, so we can get moles of oxygen by dividing by its atomic mass. And if we want to know the moles of the metal, we go to the chemical formula. So it's MO2, so that means we have 1 mole of our unknown metal for every 2 moles of oxygen. Okay, again, the chemical formula tells us the molar ratio of the two elements, 1M, 2 O's. So we divide by 2 to get the moles of M. So moles of O cancel out, and so this conversion gives us how many moles of our metal are in a 100 gram sample, which we've arbitrarily chosen as our starting point for convenience. And so this is 0.6634 moles. Okay, so that's the molar amount for our unknown M. So we put this into our formula, 0.6634. And so when we divide this out, we get 118.73 grams per mole. Alright, so this is the atomic mass of our unknown elements. Let's go to the periodic table and find one that matches up with that. So we find 118.7, so indium is 114.82, tin though, 118.7. Okay, so the atomic mass that we've determined matches up closest with tin, Sn. So we just needed to enter the symbol, which is Sn. Even if you don't realize that that's tin, that's the symbol we would enter. Okay, so any unknown element problem, we want to think about it in this context. Figure out a way to determine the atomic mass, which is the mass of the element divided by the moles, and once you have the atomic mass, match it up on the periodic table. Alright, that takes us to the end of this week. As always, if you have any additional questions or things on this video that you still don't understand, please let me know, and I will talk to you individually or address those through the Blackboard forum.